All right. Good morning or afternoon or whenever you're watching this. I'm going to do a quick introduction to hypothesis testing. We're not going to be able to cover it in as much detail as we usually would, but I want to make sure, since this is a pretty important idea, that you've been exposed to it and at least have some practice doing it. And there's one part of the take-home exam that asks you to conduct one. They take a little bit of explaining, but once we get through it, similar to confidence intervals, they work out to a pretty simple algorithm, just a simple set of steps that you perform to do it. So I'll start with the basic overview, a quick one, and then I'll post a couple of videos after this that will be examples of the kinds of hypothesis tests that we're going to do. So a hypothesis test, so this is we're in chapter 10. We're going to do two kinds of hypothesis tests. And the book will talk a little bit about two-tailed tests. I'm going to focus just on one-tailed test in the interest of time and simplicity given our circumstances. So in a hypothesis test, there's going to be some kind of claim, maybe that we're trying to disprove, or we're interested to know if something, we're trying to show that something has an effect. So maybe a company has claimed something about one of their products, or maybe we are developing a product and we want to know if it actually has an effect on the thing that we are interested in. And so in this, we'll start by naming two hypotheses. There's something called the null hypothesis. We use this H naught. And this is going to be, it's going to be a statement about the mean, right? We're only going to do hypothesis testing about the means of certain populations. And the null hypothesis will be the status quo, right? In other words, if we're testing the claim about that some company's making, it's that their claim is true. We're not going to upend their claim and say that it's false. Or if we think we have a new medicine that aids in some kind of treatment, the status quo is that it doesn't actually have an effect. So the H naught is not the thing, the null hypothesis is not the thing we are actually interested in researching. We're hoping to show the opposite of it. And the opposite of it will be the alternative hypothesis, right? This is that H naught is not true, okay? And then both of these hypotheses are going to be statements about the mean. So H naught would be something like the mean of the population is equal to some number, right? That might be the claim that's being made. And we might claim that no, the mean is actually less than that number, whatever they've said it is. Or maybe something like greater than that number, something like that, or even not equal to, though we're not going to do that case this quarter. We're also going to have to decide when we start our test what is called alpha, right? And alpha is really telling us how strong a case we need to prove to reject H naught. Remember, H naught is the status quo, so alpha is going to be the level of significance is what we call it, but it's going to be how strong a case do we need to make to reject H naught. Later on in the test, we're going to compute the probability of something happening, and we're going to, and if that something happening is very unlikely, then we'll reject H naught. And the very in that statement, how unlikely does something have to be, is defined by alpha. I always think about it this way. If I were to flip a coin in front of you and flip heads 3 or 4 times in a row, you might be suspicious that it's a trick coin, that it doesn't have heads and tails, but you probably wouldn't be sure yet. Or you probably wouldn't be comfortable calling me a liar if I had claimed that it was a regular 2-sided coin. But if I flipped that coin 100 times in a row and it came up heads every time, you'd probably be pretty confident that my coin had something funny going on with it. So alpha would be something like, how many coin tosses in a row do you need to see me flip heads before you go, there's something wrong with that coin, right? After 5 heads in a row, after 10 heads in a row, after 15 heads in a row, how many is it? So we decide that before. Now, you won't actually have to decide that. I will give you alpha in any problem I ask you to do. But typically a researcher would have to decide alpha, and they would do it before they run their experiment. So they're deciding ahead of time how strong their evidence needs to be. Okay. So once we've done that, we will, depending on our situation, there's going to be 2 different situations we deal with here. that will determine what we call the test statistic. I'll get to that in a moment. But the situations are very familiar. You've seen them before. They're the same situations we have in confidence intervals, that we are testing a population mean and the standard deviation of the population is known. Right? So we had confidence intervals where we were making a confidence interval about the mean where we knew the standard deviation of the population. Or we will test a population mean when the standard deviation of the population is unknown. Okay? So those are the two situations we're going to find ourselves in. And so when we have these situations, we'll have a very similar difference that we had in confidence intervals. Remember when we were in the situation 1, we would use z-scores, and when we were in this situation where the standard deviation of the population is unknown, we would use t-scores. The same thing happens here. So when we're in this situation, we're going to compute a z-score with the following formula. So I'll explain what each of these symbols are in just a moment. Sigma divided by the square root of n. So our z-score will be, our test is conducted by, if we're trying to test something about a claim a company makes, we might go out and take a sample and compute a sample mean. And this would be our sample mean right here, this x bar. And we take the sample mean minus the sample, the population mean. This is the status quo, the population mean given in H naught. And then we divide it by the standard deviation of the population divided by the square root of n, the sample size. So you might recognize this as coming from the central limit theorem, right? This is what we're really using is the central limit theorem here, and this is the z-score under the central limit theorem of the distribution given by x bar, okay? So we can compute a test statistic that way. If we don't have the standard deviation for the population, we compute a t-score with a very similar formula. We take that sample mean minus the population mean. Now, instead of dividing by the standard deviation of the population, we don't have that, so we have the standard deviation of our sample, which of course we have because we went out and got that sample, so we can compute this. And again, divide that by the square root of n. Okay? So these are our two test statistics. Okay? Once we compute these, we will look at the probability of getting these test statistics or something more extreme. So our last step will be to compute, well, not our last step, sorry, our second to last step will be to compute what is called the p-value. This is the probability of going out and getting a sample with the test statistic or more extreme, which is kind of a convoluted sentence. So if we were, for instance, trying to show if the alternative hypothesis was that the mean was actually less than some company claimed, we might test what is the probability of having a z-score less than the z-score we computed. Right? This z-score over here is the number that we're putting here. Or if we were trying to test if a population mean was greater than the number that was claimed, we might compute something like, what is the probability of getting a t-score greater than the test statistic? Okay, so that's just going to agree with our alternative hypothesis. So these two numbers, whichever one we compute, are called our p-value. And all we do is we compare the p-value to alpha. Remember, alpha was given in the beginning, or a researcher would decide alpha in the beginning. If the p-value is less than alpha, we reject the null hypothesis. And if the p-value is greater than alpha, we fail to reject H naught, right? Remember, alpha is how crazy does something have to be before we say that there's, how extreme of a situation do we have to be in before we say that there's something weird going on? Like how many heads in a row would I have to flip before you say that coin's not legit? So if we end up with going out and getting a sample that's more unlikely than the level we set with alpha, then we say there's probably something going on in the null hypothesis is not true. Otherwise, we fail to reject. We can't say that we've gathered enough evidence to reject the H0. Okay, I'll do a couple more videos with some examples, which hopefully will clarify some of this stuff. I know it's still a bit nebulous. I hope you've been reading the notes and the textbook as well. This is an important idea that we need to get down.